Welcome to today's video on Cambridge IGCSE Mathematics for the syllabus codes 0607 and 0580. Our topic for today will be vectors and transformations, where we will be looking at the subtopic transformations. So transformation is a general term that we use when we can manipulate a shape in either its size or position. And this cannot be just manipulating a shape, but it can be even a point, a line, or any other geometric figure, which we are changing the size of or the position of, and then that would be known as a transformation. Now, the original shape of the object that we have would be called the pre-image, and then the final shape and the position of the object after our transformation is called the image under the transformation. We have four common types of transformations. This is translations, rotations, reflections, and dilations. Dilations are also called enlargements. And in this video, we'd also be looking at a separate type of transformation, and that's called a stretch. The first transformation that we're going to be looking at is a reflection. Now, the reflection of an object across the mirror line produces the mirror image of the object on the other side of our mirror line. And when we perform reflections, what we need to remember is that every point on the object that we start off with is the exact same distance from the line of reflection or from the mirror line as the matching point on the other object. So for example, if we look at this diagram over here, I can see that my purple triangle is a reflection of the blue triangle, and it's a reflection of the blue triangle in the line x is equals to 2. So in this case, x is equals to 2 is acting as a mirror line. And if I look at the distance of each point away from the mirror line, then that's going to be the same distance as the object. So I can see that here, this specific point is 3 units away from the mirror line. And here the triangle in purple is also the same. It's 3 units away from the mirror line. And every vertex of my triangle is going to show that same relationship. The distance from every point of my object from the mirror line is going to be the same as the distance from my other object to the mirror line. The next transformation that we're going to be looking at is a rotation. Now, a rotation is when we are turning an object about a specific point. And whenever rotations are described, we need to be making sure that we're describing or we're giving the angle of rotation, the direction of rotation, and the direction can be either clockwise or an anti-clockwise rotation, as well as the center or what we call the point of rotation. So when we describe rotation, we need to be talking about these three things. When we have clockwise rotations, then this is generally shown by having angles that are negative. So an angle of negative 90 degrees means that we are rotating this shape in the clockwise direction by an angle of 90 degrees. And then on the other hand, if you have anti-clockwise rotations, then our angles are usually denoted as positive. So if you see a rotation of 90 degrees, and this is positive 90 degrees, then this means this is an anti-clockwise rotation. So in this example here, what we are trying to do is we're trying to describe the rotation of our purple triangle from the blue triangle. So we're starting off with the blue triangle, and then we're trying to rotate this, and then we get our purple triangle. So in this case, the blue triangle, we can say this is our object, and the purple triangle would be our image. And to get the blue triangle to move to the position or transform to the position of our image, that's the purple triangle, what we need to do is we need to rotate this blue triangle 180 degrees clockwise about the center of rotation, that's 2, 1. So we have a point of rotation, we have denoted the angle of rotation as well as the direction of rotation. Now, in this example, something that you need to notice is that we've said that the angle of rotation is 180 degrees. Whenever we have angles of rotation that's 180 degrees, this really doesn't matter if we rotate our shape either clockwise or anti-clockwise because we're going to end up in the same position either way. And this only works for an angle of 180 degrees. And for all the other angles that we have, then our shape, that's our object in our image, is going to be in different positions if you rotate it clockwise or anti-clockwise. We'll also go ahead and see how we can rotate shapes given tracing papers. So in this example, what we're going to be doing is we're going to be rotating this shape 90 degrees clockwise about the point 2, 2. So we know the point 2, 2 is over here on our coordinate grid. And we have a triangle here that we're going to be rotating 90 degrees clockwise. Just to make a point here, we have been given 3 pieces of information. Like we've already discussed, we know the angle of rotation, we know the direction of rotation as well as the center of rotation. That's a point 2, 2. So to begin with, what we're first going to go ahead and do is we're going to draw a line here that's going to help us get the angle that we need. And this can help us with any angle that we want. It's 90 degrees here, but this can also help us when we want to rotate a shape that's 45 degrees or 50 degrees or 180 degrees or whatever angle that might be. So we're going to draw a line, a horizontal line at our point of rotation. And then what we're going to do is we're going to place tracing paper on top of that. And the next thing you're going to do is you're going to make sure that you're drawing that line that you drew on your paper. You're going to draw that on top of your tracing paper as well. And then you're going to keep, or you're going to place the point of your pencil at the center of rotation. In our question, this is a point 2, 2. We're going to place our pencil over here. And then what we're going to do is we're going to slowly rotate our tracing paper to the angle that we require. Now in this case, we want to rotate this to 90 degrees. So I'm just going to go ahead and do that. And I know this is a 90-degree angle because this is the angle, this is a line that I initially drew. And this line that I initially drew is now at 90 degrees to the line that I drew on tracing paper. So once we've done that, once we've rotated this 90 degrees, and we can also see that I rotated my tracing paper clockwise, this position where the triangle is on the tracing paper is now the position of our image. So we started off with this object here, and now we rotated it 90 degrees clockwise. Next, we're going to be looking at translations. Translations is a transformation that describes the movement of your object in a straight line. And this movement can be a horizontal movement, or it can be a vertical movement, or it can even be both a horizontal as well as a vertical movement. So your object can be moving to the left or to the right, or it can be moving up or down. And this can be described by a vector. So let's look at the example that they've given us here. They've said the triangle ABC has been transformed to the triangle A-B-C- by a translation of 7 squares to the right and 2 squares up. How would we know this? This is our object over here. And if we want to see how it has been translated, what we're going to do is we're first going to go ahead and look at how it has been translated horizontally. So I can mark corresponding points on the object and the image, and I can see that this has gone 1, 2, 3, 4, 5, 6, 7 units towards the right, as well as 2 units upwards, which gives me a translation vector of 7, 2. How do we get this? When we use our translation vectors, you need to remember that the number at the top is always the horizontal movement. and the number at the bottom is the vertical. If you instead don't move towards the right, but you move towards the left, then you need to remember that this is going to change into a negative value. And similarly, if you're moving down instead of up, then this is also going to change into a negative value. So there we go. This is how we translate objects using a vector. We might also be asked to find the magnitude of a translation. And one way to see what the magnitude is to draw out the triangle that's produced by the translation. So this is going to be a triangle here, which has 7 units as the horizontal component and 2 units as the vertical component. And then the magnitude of our transformation would be the length of the hypotenuse that's being produced. And by using Pythagoras' theorem, we would be able to find the length of this hypotenuse. So if this is 7 and this is 2, then the length of this hypotenuse would be the root of 7 squared plus 2 squared. And in this case, our answer is the root of 53. The next transformation that we have is enlargements. Now, enlargements are the only transformation that modifies the size of our object, and this can either make your objects bigger, or they can also make your objects smaller, and that's something that we need to remember. And whenever we describe enlargements, we need to make sure that we have been given the scale factor as well as the center of enlargement. So if we look at this example over here, we have been given the letter T that has then gone and been enlarged by a scale factor of 2. What we mean by this is if something is getting enlarged by a scale factor of 2, it's doubling up in size. But we also have a center of enlargement, and in this case, O is the center of enlargement. So the size of the PACB here has been doubled in size using the center of enlargement O here. Now let's go ahead and see a quick simulation on what would happen when we change the scale factor of enlargements. So over here, the object, you would be able to see the triangle here in green, and then I'm also going to show you the enlarged image in brown. If I have scale factors of enlargement that's greater than 1, and over here, we're going to be denoting the scale factor of enlargement. If these scale factors of enlargement are greater than 1, then what you would be able to see is that your shape keeps on getting bigger. It's getting bigger than the original. So this is my object in green, and this is my image in brown. And I can see that when the scale factor of enlargement is 2, then the image is double in size compared to the object. And something else that I can also notice is that if I look at the corresponding vertices of my shape, the vertices of my object and the vertices of the image, I can see that they are both on the same side as the center of enlargement. So in this example, we're using the center of enlargement as the origin. That's the point 0, 0. I could also have center or scale factors of enlargement that's less than 1. And if I decrease my scale factor of enlargement to values that are less than 1, then something that we would be able to notice is that our image now becomes smaller than the object. So I can see in this case, my image is smaller than the object. This is using a scale factor of enlargement of 0.25, that's 1/4. And if I compare the sizes of my object with my image, I can see that my image is now 4 times smaller than the object. We also need to know what's happening to our object and the image when we have scale factors of enlargement that are negative. And when we have negative scale factors of enlargement, what we would be able to see is that our shape is actually getting enlarged, is getting bigger, and what is going to be different, however, is the positions of the corresponding sides. If I look at this vertex here, this is A, and then this is the same corresponding vertex on the image. We've labeled that as A dash. I can see that the point A on the object and the point A dash on my image, they're both on the opposite sides of my center of enlargement. So they are no longer on the same side as my center of enlargement, but they go on to opposite sides. So having negative enlargement just means that you are still enlarging your shapes, but this enlargement is going to be on the opposite side to the center of enlargement. Let's go ahead and look at an example. So in this question, they want us to enlarge the shaded shape by a scale factor of 2 above the point 0, 0. So this is the shape we have. We have a triangle, and we're going to enlarge it about the scale center of enlargement, that's 0, 0. That's our origin over here. And to begin with, what I'm going to do is I'm going to draw a line from the center of enlargement to one of my vertices. So I'm just going to draw a line to the vertex that I've labeled B. And I can see that to draw this line, I have to move 1 across and 2 units upwards. Because we are enlarging our shape by a scale factor of 2, I'm now going to extend this line so that it's double those measurements. So instead of going just 1 across and 2 up, I'm going to go 2 across and 4 units upwards. So I can extend that line until I reach this point here. So that's 2 across and 4 upwards. And then I'm going to mark this spot here. So this point B has now been mapped onto this point over here. And we're going to go ahead and do that for all of our vertices here. So let's do this for A as well. For A, I can see that I have to go 1 across and 1 down. Because we are enlarging this by a scale factor of 2, I'm going to double that. And I'm going to go 2 across and 2 down. So 2 across and 2 down. And I'm going to end up in this position here. I'm going to go ahead and mark that point over here, the X. And then finally, we're also going to do that for the point C. To get from our center of enlargement to the point C, I can see we're going 3 across and 1 down. I'm going to double that, and I'm going to go 6 across and 2 down. So I'm going to reach this specific point here. So B gets mapped to B dash, A gets mapped to A dash, and C gets mapped to C dash. And then I can just go ahead and connect these points here. And this is going to give me my enlarged shape. So this shape that I have over here is the enlarged shape. We can remove these construction lines after they're completed. And this is our enlargement. The final transformation that we're going to be learning about is a stretch. Now, a stretch is when we have an enlargement of a shape, but this enlargement is taking place just in one direction. So this can be enlarged horizontally, or it can be enlarged vertically. And when we describe the stretch of a shape, we have to mention the direction of the stretch along the invariant line, as well as the ratio of corresponding sides and the determining stretch factor. So just to understand a little bit more about stretches, I'm going to consider this diagram over here. So the object has a dark blue outline, and the image I'm going to show you in green. So if I stretch this image horizontally, what's going to happen is that the image is going to increase in length horizontally, but its vertical length does not change. And if this happens, I can see an enlargement that's taking place only in one direction, and in this case, horizontally. Then this would be known as a stretch. On the other hand, your image can also be stretched vertically. And to do that, what we're doing is we're doing something like this. We're taking an object, but we're stretching it just vertically. And then the image would look something like this. This is also a stretch. Let's look at another example over here. So in this example, our object is the rectangle ABCD. And then what we're going to do is we're going to stretch this rectangle using a stretch factor of 2 that's parallel to the y-axis with our invariant line being y is equals to 0. Now, the invariant line is going to act as our reference point, just like how we had a center for enlargements and rotations. We would have an invariant line for stretches. So y is equals to 0 is this line over here. This is going to be acting as our invariant line. And then our stretch factor would be parallel to the y-axis. And we're going to go ahead and stretch this rectangle. Because the rectangle is being stretched by a factor of 2, this means that we're going to increase its length by 2. So it's going to double in size parallel to the y-axis. So this is what's going to happen to this. And then our image is going to be the rectangle A dash, B dash, C dash, D dash. And this is what we're going to get at the end of our stretch. In this example, what we can see is that the object was lying on our invariant line. And when we perform the stretch, all of the points that were on this invariant line did not change position. We can see that after stretch, our image is a distorted version of our object, and they are not similar in shape, neither are they congruent. We can also combine transformations and then denote these specific transformations by symbols. For example, we can let the symbol A denote reflection in the line x is equals to 3, and then let B denote the translation using the vector 2, 1. So if we begin with an object, we can first reflect it using the transformation A. That's a reflection in the line x is equals to 3. And here we can see that we are taking our object, that's the triangle, this first triangle here, then we are reflecting it in the line x is equals to 3 to obtain our image, that's the second triangle in yellow over here. And then what we can do is we can use this and then we can translate it in our second step. So we can translate triangle 2 with the vector 2, 1. So we can move this 2 units to the right and 1 unit upwards to obtain our final answer. That's this triangle 3. Now, this combination of transformations would be denoted by these symbols here. And what this tells us is that we're first going to perform transformation A on triangle 1. And then using the image that we get in that transformation, we're going to perform transformation B on it so we can get our final image, that's triangle 3 in this case. Finally, we're going to learn about inverse transformations. An inverse transformation is the transformation that causes our image to return back to its original object. So we're just undoing the transformation. If we have a specific vector t, then the inverse transformation would be denoted by the symbol t to the power -1. And if you perform the transformation t to the power -1, then we would return our image back to the object. So if we have the translation, if we have a translation, then the inverse translation would be basically taking the vector that you use to describe your translation and then getting the negative of it. So here we have the vector 2, 1. And if I get the negative of this vector, this is a vector -2, -1, then this vector would give me my inverse transformation, which would be able to be performed on my image to take it back to its original position to show me what my object was. If we had a rotation of 90 degrees clockwise about the point 0, 0, then the inverse transformation of this would be a rotation of 90 degrees anti-clockwise about the point 0, 0. So you can see that when we have to figure out the inverse transformation for a rotation, the angle and the center of rotation remains the same. The only thing that changes would be the direction of rotation. When we have reflections, the transformation and the inverse transformation would describe the same thing. If you want to work out the inverse transformation of the reflection, you just have to perform the same reflection again. Let's go ahead and look at an exam type question based on transformations. In this question, it asks us to describe the transformation of our shape ABCD. I can see that the shape ABCD is a square here, and it has been transformed to the image A dash, B dash, C dash, and D dash. If I go ahead and compare the sizes of my object and my image, I can see that they're the exact same size. And they're also in the exact same orientation, which gives me an idea that this is probably going to be a translation, which means my object has just moved on the coordinate grid to a new position to form my image here. So I need to figure out by which vector has this been moved. And to do that, I'll first figure out the horizontal component of the translation, and then I would work out the vertical component of my translation. To do this, I'm just going to first go ahead and highlight corresponding vertices. I'm just going to focus on the vertex D and D dash here for the sake of this example. And I'm going to see that my vertex D has moved 6 units to the right, and then it has moved 2 units upwards. Because it's 6 units to the right, I know that my horizontal component should be positive 6, and because it's 2 units upwards, I know my vertical component of my vector should be positive 2. So the answer is this one over here, 6, 2. So there we go. That's our video on transformations. Thank you.